Hello everyone, I am Swathy Manohar, an assistant professor in the Department of Civil Engineering at IIT Bombay, India. Thanks to Rilem for this wonderful opportunity to have this interaction happening here. Me and Anupama will broadly talk about the significance of understanding salt crystallization from the perspective of conservation of heritage structures. I will focus more on the key material properties that could enhance salt crystallization resistance in historical masonry structures. I'll start with a brief bio of myself. I did my bachelor's in civil engineering from Kerala, India in 2013, followed by master's from IIT Roorkee. Then I did my PhD from IIT Madras, where I worked on understanding degradation mechanisms in historical structures, basically salt crystallization phenomena, followed by a brief postdoc at IIT Madras and an early career fellowship at IIT Gandhinagar. Then I joined at IIT Bombay as an assistant professor in 2022. I had a brief stint at ETH Zurich as a visiting faculty in September to December 2024 as well. Now I'll start with a roadmap for next 15 to 20 minutes. I'll talk about what is salt crystallization, why does it happen. Then I'll go more into the role of pore system of the materials in governing salt crystallization. We will do this with the basis of 3 different case studies, one on building stones, fired clay bricks, and lime mortars. Starting with the impact of durability. So this is the big temple or Brihadeshwara temple in Tamil Nadu, India, which is made of granite, constructed in 1010 AD and is still in sturdy. But if you look at modern structures, we see damages in less than 10 years or even much lesser than that. The emphasis is that it's not the strength that determines the damage, it's the durability, which is basically because of the porosity and permeability of these structures. This response differs with respect to the exposure condition. If it's because of salt, wind, air pollution, so there are different durability problems associated with different materials. And if we understand the mechanism of these degradation phenomenon and the relation with the microstructure or porosity and permeability, can we actually scientifically design building materials for longevity? This is a potential interesting question that we will be able to answer by end of this presentation. Coming to salt crystallization, the first disclaimer is that it is one and same as physical salt attack, especially when we talk about sodium sulfate. The general name of sulfate attack is generally chemical sulfate attack. But in physical sulfate attack or physical salt attack or salt crystallization, you will not have any chemical interaction between the salt and the substrate material. It's only the chemical reactions within the salt or salt with water. What are the common manifestations of salt crystallization? Efflorescence, the white patches you see, powdering, blistering, and all of this is because of salt crystallization, which is salt and water from the atmosphere getting into the pores of the system in form of salt solution. What happens on evaporation? They slowly come out, the vapor will escape out and salt will precipitate on the surface, which is efflorescence or the white patches you see. If the evaporation rate is much higher, vapor could escape easily directly from the pores and the salt will precipitate inside the pores. This is more damaging because now the crystals can create something called crystallization pressure to the pore walls, which could damage your material. This is called crystallization, which is identified as one of the most prominent damage mechanism in historical structures. Not only in stone or brick structures, but even in concrete structures, this is prominent. And you see examples of concrete, stone, as well as brick structure, which are susceptible or to salt crystallization damage here. And you see the extent of damage it can go to. What is the mechanism of salt crystallization? I'm going to show this based on one of the SEM images from one of the fired clay brick samples of mine, which was found to have larger round pores. So in large round pores, with subsequent dry wet cycling, salt solution gets into and get more and more concentrated or more saturated. When it reaches supersaturation, the crystal precipitates. And you see, this is a large round pore. The crystal is free to grow in all the directions. There is no restraint or constraint for the growth. So it will not cause any pressure to the pore walls. It's free, stable, settled there growing. So in larger pores, crystals are free to grow in all directions, so it doesn't cause damages. This is not the case in a smaller pore. So here you are seeing a smaller cylindrical pore with pore walls on the sides and the crystal being stabilized inside. The crystallization pressure will arise here based on the thermodynamic balance of Gibbs free energy. I want you to look at the crystals first at this end. The ends of the crystal are having a hemispherical shape, hence the curvature is very large there. There will the solution touching that curvature should have a very high supersaturations to balance the free energy there. The supersaturation of the solution is going to be very high in the water or in the solution there to balance this high curvature. But if you look at this side, the curvature is almost half as that of the curvature at the hemispherical ends. So the curvature is very small. But the supersaturation of the same solution is already very high. So the Gibbs free energy associated with this excess unwanted supersaturation at this place will generate some crystallization pressure to be acting on the pore walls. Now this crystallization pressure and the smaller curvature is going to balance the high supersaturation here. Now you have crystallization pressure on the pore walls. This will generate hoop stresses around the pore walls. If the tensile strength of your material is higher than this hoop stress generated, then you will not face damage. But if the hoop stresses are going to be higher, you will have cracks and damages initiated there. That is how crystallization pressure causes damages in your system if you have smaller pores in the system. Now we look into the case studies. First is a case study of a building stone, which is a highly porous limestone called coral limestone or coral stones. This is a case from Sri Ramanatha Swami Temple in Rameshwaram, India. And what you see here is X-ray diffractogram and scanning electron microscopy of the material. So the speciality of this particular stone is that it's very, very light. The density is very close to water, so it can actually sometimes float in water as well. When we look more into the microstructure, we found that the crystals, the quartz crystals are surrounded by a lining called magnesium calcite, which had a flowery petal-like morphology, which was making the overall material much lighter and porous. And because of this larger pores in the system, when we subjected this particular stone to accelerated salt weathering also, we saw that it was having very high resistance to salt weathering. Now you know why. Salt can easily go and get deposited in the larger pores and there are not much of smaller pores in the system. This would help in not having damages in the system. Another interesting information or interesting observation from this particular stone was that there are larger magnesium calcite, larger porous magnesium calcite lining here. There were also smaller porous calcite here. But when we looked for the precipitation of sodium chloride crystals, we saw that the crystals were only in the larger magnesium. These are the crystals. They were seen only in the larger magnesium calcite pores and not on the smaller pores of calcite, which is in the bottom. The reason is that there is always something called preferential deposition of salt precipitation. This is because when you are having connected large pores and smaller pores, the supersaturation will drain from the smaller pores to larger pores and crystals would go and deposit in the larger pores, pairing the smaller pores. So this also would be one reason for the high salt weathering resistance of the coral stones. Now we go to the second case study, which is fired clay bricks. So these are all porosity data of different fired clay bricks of different porosities. What you see here in the histogram for one sample, for example, V1 is out of 100% porosity, we have divided it into porosity of pores and different size ranges. For example, for V1 sample, the blue color, which is 30%, is the macro porosity, pores between 110 micrometer, and the top is the microporosity. Everything in this red boxes are the same samples before, which are after weathering. So this is V1 before weathering and this is after weathering. What I want you to see is the last two cases, which is sample C1 and C2, which are having larger pores in C1 and smaller pores in C2. So after weathering, you see that in C1, the macropores are remaining same. There is no much changes in the macropores. Small redistribution occurs in the microporous range. Whereas in C2, macroporosity increased so much, almost double. And now you see how the manifestation looked like. C1 did not have much damage other than superficial mass loss, which is progressive. But in C2, total crumbling of the sample occurs. Do you want to know why? C2, if you look at the microporosity, see it was close to almost more than 15% of microporosity. But a C1 was having microporosity much smaller. So now we already know that salt crystallization will happen only in these micropores which are damaging. And this particular material is having large amount of microporosity which resulted in damage, and the damage can you can see here how more number of cracks and fissures are being formed in the material. That's why the macroporosity is increasing. The major conclusion from this slide is that it is if the microporosity is higher, which is pores less than 1 micrometer, the more is a susceptibility to damage. So it's not the total porosity that we should be worried about, but it is the percentage of microporosity in a system. We also compared the behavior of the bricks with different salts, sodium sulfate and sodium chloride. Also, we looked at the efficiency of different coatings and uncoated samples. Here, the sample which is having small pores and more susceptible to damage is coated with two different coatings, silicon and acrylic siloxane based coating. You see that the uncoated, the red ones, are getting damaged at say 20-22 cycles. But silicon based coating gets damaged even before that. Acrylic based coated samples are prevailing to be in good condition even after a number of cycles. This is because we see that one particular type of coating is behaving, is happen to see that it's worse than leaving the sample uncoated. This is case of sodium sulfate, which we just discussed before why this was happening, crystallization pressure. In case of sodium chloride, the uncoated samples, the red one is not damaging even at 10 cycles, same with acrylic siloxane based coating. But when we are having a wrong coating, we could see that damage is initiating early. In case of sodium chloride, we are not seeing damage in normal cases because sodium chloride is not a salt which has high crystallization pressures. Also, it has smaller ionic sizes which can go to the smaller pores and get deposited, not causing damages in the samples. Now, if we are comparing the efficiency of different coatings, we also saw that the second one, which is a silicon-based coating, is performing very bad because probably it would be acting as a complete sealant over the samples, which would create stresses inside the material and would crack up, open up. But when we are having acrylic siloxane based coating, which has a tendency also to form cracks during the exposure period, would help in releasing the stresses out. So if we are giving a right coating which is compatible to particular material and salt, then it would perform better in long term. Same is the case with sodium chloride as well. So the takeaways are, with sulfate, it is a crystallization damage. But in case of sodium chloride, only salt deposition happens inside the material in the micropores. Coming to the coating, sodium sulfate exposure in microporous bricks, which are more damaging, needs a breathable coating. It should be a breathable coating compatible to the matrix, which is found as acrylic siloxane based coating here. Why is sodium sulfate salt super damaging? This is the same reason why we are choosing sodium sulfate in all accelerated weathering tests as well. There are two stable phases of sodium sulfate. One is thenardite, which is sodium sulfate anhydride, and one is mirabolite, which is sodium sulfate decahydrate. The direct transformation of thenardite to mirabolite, which was believed to be in the earlier cases, is actually not happening because of some lattice mismatch. Therefore, transformation occurs by a process called dissolution mediated crystallization, which I'll explain in next slide. The factors influencing are temperature, concentration of the solution, and humidity. These are the phase diagrams of sodium sulfate, where you can see that mirabolite, which is sodium sulfate decahydrate, will form only in some particular temperature and humidity, which you can easily assess from these graphs which are available everywhere. And these are the thenardite. The green colors are denotes the thenardite, which also happens at say larger temperatures and higher concentration. Now I'm explaining what I told in previous slides in a bit more simpler way. At temperatures more than 32.4 degrees Celsius, based on the previous phase diagrams, only thenardite is stable and mirabolite is unstable. So green is a thenardite. So at whatever the relative humidity is, if the temperature is higher than 32.4 degrees Celsius, mirabolite will go and convert to thenardite and water. So you will see only thenardite in those systems. When the temperature is reducing to less than 32.4 degrees Celsius, if the relative humidity is high enough, then it is mirabolite. But if the relative humidity is getting reduced to something less than something called relative humidity critical, then thenardite is going to be stable. So if the relative humidity is smaller, then again mirabolite will convert to thenardite. Thenardite will remain thenardite at lower temperatures. But at lower temperatures, if the relative humidity is higher, then mirabolite is the stable material, stable phase. But then thenardite cannot directly convert to mirabolite because of lattice mismatch. What actually would happen is thenardite will get dissolved in water and form aqueous Na2SO4 solution, and more thenardite will come and dissolve in that and form supersaturated aqueous Na2SO4. When it is supersaturated, you would get mirabolite crystals precipitating out of it. Now you would have more mirabolite crystals in the system, which are larger in size, which are expansive in nature, which would create crystallization pressure at the pore wall, and it would cause damages. Even though this is our theory, this has been experimentally observed and investigated in one of our case studies, which we did in a brick fort wall in Trankbad in Tamil Nadu, which was severely damaged because it was right exposed in the seashore with marine conditions and very high relative humidity. The last case, which is of lime mortar, where we looked at the pore sizes and salt weathering impact in lime mortar. So we had two different sets of lime mortar, standard ones with just lime, aggregate and water, and modified lime mortars with organic additives. In organic additives, we use cane sugar, which is otherwise called jaggery, which is a traditionally common organic additives which are used in India. The use of any carbohydrate-rich organics like jaggery or cane sugar appears to greatly improve the fresh and durability properties of lime mortars. That's why we were using it from the ancient times, but the phenomenon or the dosages are not clearly known. They are told to have slow carbonation during the initial period before the pore solution dries, thus providing good conditions for the diffusion and dissolution of larger amount of CO2 to the inside. So they will go and coat around the calcium hydroxide particles, thus inhibiting the initial nucleation of CaCO3. Thus also CO2 can easily get into the system and have better carbonation. So this is a live microscopic image where you can see of the fresh sample, where you could see calcium hydroxide particles are being surrounded by a layer, which is because of the absorption of the organic additive to the system that would prevent initial nucleation. Now, when we subjected the samples which are modified with organic and without organic to artificial salt weathering, we saw that the black line, which is controlled sample, lime sample without organic, failed at around 25 to 30 salt weathering cycles. But when we had organic in the system or jaggery in the system, it was performing well even at larger number of salt weathering cycles. Even though it was not looking great, it was having high amount of efflorescence, which is actually not damaging to the material. It was precipitating outside the material. This probably could be because of the presence of larger pores, uniform pores, better and uniform carbonation in the system, which is having when you are having jaggery or carbohydrates within the system, which is actually to be investigated more. And this is our illustration from the understanding that we developed. The first one with pure airline mortar could act as a salt accumulating system with smaller pores. Salt could go and accumulate and cause damage because of crystallization pressure. But when you are having modifications in the system with organic addition, especially fermented jaggery, and you are having larger pores generated in the system, which are uniform, and it would prevent salt accumulation, but instead salt transporting could happen, which would enable in the formation of efflorescence on the outside and prevent subflorescence formation. This also opens the possibility of exploring improvements in the use of airline mortars for conservation practices by incorporating locally organic additives. Summarizing all of that I have talked so far, the parameters that are influencing the material salt crystallization resistance is divided into two: pore size and connectivity. In pore size, now I hope you know C1, C2 were the samples representing larger pore and smaller pores. Larger pore samples always would behave better with salt crystallization because salt can grow in all directions in a larger pore. It will not cause crystallization pressure, but in smaller pore, it will cause crystallization pressure and would damage the pore walls. Coming to the second parameter, which is the degree of interconnection. Even if you have smaller pores in the system, if they are well connected with a larger pore, supersaturation draining would occur and the crystal would always have a preferential precipitation in larger pore. Again, if it is precipitating in larger pores, you will not have any damage. Now, the last factor is the grain strength. Even if everything is supporting crystallization, formation of pressure, but if the pressure generated, which is creating hoop stress, is lower than the tensile strength of your material, then again you will not have a damage. So if the material's grain strength is high, the higher than the crystallization pressure, then again you will not have any damage in the system. Now, this is my last slide. The 3 points worth remembering of this presentation are: first is, it's not the total porosity, but the pores between 1 micrometer and zero point 0.2 micrometer, which is the microporosity, determines the salt crystallization behavior of a material. Second point is, in sodium sulfate salt, crystallization pressure would be generated owing to high supersaturation, which could lead to more damage. But in sodium sulfate, it is mass deposition predominates, where sodium chloride crystals would go and precipitate in the pores, which would increase the mass of the system. Thus, decreased porosities and less damage would be resulting. Thank you very much for your attention. Now, since we looked at stones, bricks, and mortars separately, Anupama will take you to sandwich samples where you have masonry units as well as mortars together, and you will understand how they together would behave in a salt crystallization environment. Thank you very much.